Okay, we've completed chapter 12, and so in this video, we're going to go through the review exercises at the end of the chapter. So chapter 12 was about the regression line. Now, but we learned about the general idea of the regression line and just regression in the previous two chapters, chapters 10 and 11. So what chapter 12 was really about was thinking about the actual equation of the regression line, both from the perspective of the fundamental regression method that we learned in chapters 10 and 11, but also from another perspective that you could calculate this equation, that perspective being the method of least squares, where when analyzing the method of least squares, we learned that the regression line is the unique line that you can draw through the scatter plot data points that minimizes the RMS of all of those data points with respect to the line. Now, but it was important to note that the least squares regression line and the fundamental regression line that we learned are the same line. However, it took looking at the specifics of the method of least squares to see that, in fact, this line was the line that minimizes the RMS. So if you have some scatter plot that you're going to do a linear regression with, then there's an infinite number of lines that go through the point of averages that you can choose for the regression line, right? However, there's one unique line that goes through the point of averages that has the lowest RMS. So you take the sum of the squares of all of the vertical distances, if the vertical variable is the output variable, these vertical distances from the line. That RMS value, the regression line, is the one that has the lowest RMS value. Okay, then we also talked about in section 3, we talked about the idea of thinking about if the regression makes sense or not. So from one perspective being, is the data linear? Is the scatter plot linear? So we can think about that as, is the scatter plot football shaped, homoscedastic? But from a more difficult perspective, a difficult to comprehend perspective, being that, are there confounding variables at play to where even though the data might be homoscedastic, it might have let's say, a high correlation coefficient and a low RMS, are there confounding variables that suggest that the resulting linear regression that you perform doesn't make sense? And as we talked about this, it's confusing because we're not just talking about from a causation standpoint, but even an association standpoint, right? So if that confused you a little bit, then make sure you go check out the previous video where we talk about all of this. Okay, so let's go ahead and now go through the review exercises. Okay, first problem, find the regression equation for predicting final score from midterm score based on the following information. Okay, so if we come here, there's the average midterm score, there's the average final score, the standard deviation is the correlation coefficient. We want to find the regression equation for predicting final score from midterm score. So midterm score is the input. Okay, and again, we've done this before many times in the previous two chapters. The only difference here is they're asking us for the explicit equation. That's the only difference. And so this is really not that difficult if you're comfortable with algebra and equations of lines. Then this is really not that difficult because we've got a point and a slope. Okay, the point that this line goes through, we know that any regression line is going to go through the point of averages. So the point of averages is, let's see, so the midterm score is the input. So this is X average. And the final score is the output. So this is Y average. So there's a point, right? Now, what's the slope of the line? Well, we know exactly what the slope of the line is. It's R sigma Y over sigma X. So R is 6/10. So 6/10 is 3/5. Okay, now r times sigma y is 20 over sigma x is 10, so this is just 2. All right, and this is the slope. So what we've got is 6/5. Okay, so now just the point slope form of a line. You do, it's y minus y1 is equal to m times x minus x1, right? You got one point, that point is the x1, y1, and a slope, m. So let's see. Y minus y1 is 55. Oh, yeah, what are the units of this slope? The units would be final score per midterm score. I'm not sure what the units of that are. Whatever the units of a score is. For every 5 points you got on the midterm, you got 6 points on the final. That's the idea. So y minus 55, y minus y1 is equal to m times x minus x1. So y minus 55 is equal to 6/5 x minus, so 6/5 times 70 is 84. Okay, now minus 84 plus 55 is minus 29. So y is equal to 6/5 x minus 29. And there we go. You input a midterm score, you get out a final score. That's the regression equation. Okay, for women aged 25 to 34 in the Haynes 5 sample, the relationship between height and income can be summarized as follows. Okay, here's the data. What is the regression equation for predicting income from height? And then what does the equation tell you? All right, well, we can think about how they're relating height and income, which is kind of a weird association. I mean, unless it's something to do with like sports, but in general, it's a weird association. Well, I don't want to say that. No association is weird, but the causation is kind of questionable. Okay, well, let's go ahead and just get the regression equation, which could be completely legitimate, again, because I don't mean to say that the association is weird. An association can be weird and it can still be completely legitimate, right? Because association and causation are different. All right, so let's see. We're predicting income from height. So this is y average. This is x average, predicting income from height. Okay, now let's see. The slope is going to be, you do the r sigma y over sigma x. So let me do the calculator here. R times sigma y, 20,000, over sigma x. Is that right? So 1,600. That's, and we want to think about the units. So $1,600 per inch. For every 1 inch in height, you increase. Then you increase $1,600 in income. Is what the association is telling you. Okay, so there we go. So we've got y minus y1 is equal to m times x minus x1. Okay, so we can do, let's see, 1,600 times minus 64. Okay, and then if we add to that 21,000 minus 81,400, so we've got y is equal to 1,600x minus 81,400. Okay. So you input a height and it gives you an income. All right, now what does the equation tell you? Well, okay, we talked about how how deep you can look into a regression line is going to depend on if it's coming from an observational study or a controlled experiment. And if it's a controlled experiment, well, then how well is the control? So really what you're, in essence, what that's asking is, are there confounding variables? And if so, how confounding are they? Okay, and I believe this is an observational study. And so in general, unless you can sort of prove that it's an observational study, but the confounding is not too extensive, then in general, you can only look at an equation like this based on what it is, in the sense of, or what it's based on, in the sense of the data points that this is based on. If you gave me this is women, a woman from this study, and you said, okay, here's this woman's height, can you now predict her income? I can make a prediction based on that, a good prediction. But if it's too observational, too much confounding, then you can't really go too far with trying to make kind of like predictions. Okay, if we pick some other random woman in this age group that wasn't a part of this initial study, can you predict her income? I mean, that might work. I mean, that's kind of more advanced statistical. That's a more advanced statistical topic, but for the moment right now, just we're thinking about in general, you won't really have much confidence in doing something like that when it comes to an observational study. Again, bringing in an outside data point that wasn't a part of what you used to make the regression equation, or doing things like taking the data points that are within the study itself and thinking about, okay, if I made some changes here, if we did this with this group of people, then the regression equation says that this would happen. You can't really do, you're not really flexible to do stuff like that if there's too many confounding variables present. Okay, for men age 18 to 24 in the Haynes 5 sample, the regression equation for predicting height from weight is as shown here. Height from weight, okay? Height is measured in inches and weight in pounds. If someone puts on 20 pounds, will he get taller by this amount? If not, what does the slope mean? Okay, the answer to this question is obviously no. Okay, but this is a little bit confusing in light of what we talked about in the previous section, in saying that does the regression make sense? Because it's not like, so the reason why the answer is no here is not necessarily because the regression doesn't make sense, or like because this is an observational study. No. You can have a scatter plot, a regression to where the correlation coefficient makes perfect sense. Everything is statistically great. You have plenty of data points. You've removed all confounding, right? Let's say it's like a controlled experiment. Okay, and so what that means is that if that's the case, that means the association makes sense. You can say the association makes perfect sense. But even just because an association makes perfect sense doesn't necessarily mean that the causation is going to make sense at all. Okay, what we talked about in the previous section was that it was cases where the association happens to not make sense, and that's only going to come about because you haven't done enough data points. You haven't looked at the big picture enough to where it seems that, well, look, it's a linear relationship, right? The correlation coefficient's good, but there's unanswered questions here that to where what you're looking at isn't really reality. But if you've done a good experiment, if you've accounted for the big picture, if you've accounted for any confounding issues, and you're getting a nice homoscedastic football-shaped scatter plot, and you do a regression line through it, well, then that association makes sense. I don't care how ridiculous it is if the association is the temperature outside to what's playing on TV, which I guess when you get that ridiculous, you would have to think that you haven't accounted for certain confounding variables. But if you truly did do a legitimate statistical study with plenty of data points and whatnot, then the association makes sense. But again, it doesn't mean that the causation is going to make sense. So in this case here, it's more of the perspective you're looking at this from. yes, the causation makes sense from one perspective if we're thinking about, well, the taller a person is, the more they're going to weigh because they're just a bigger person, right? But then it doesn't make sense from the perspective of, okay, if someone goes, if I take a data point and I move that existing data point, it's going to follow the regression. Well, that doesn't make sense. From the perspective of that causation, it doesn't make sense. No one's going to go, if you go gain 20 pounds, you're not going to grow in height. Or if you lose weight, you're going to shrink in height. That's not what the causation is about. That's not where the association is coming from. So what does the slope mean? The slope is just saying what I just mentioned. It's saying that, look, you have a person that is taller, then in general, that person is going to weigh more because they're just a bigger person. It has nothing to do with the biological association between eating and growing. And I guess unless you're dealing with children, but even then, children are growing really, as long as they don't starve, they're growing, right? So, okay, so you really need to reword this question to get the causation correct. The causation that is ingrained with the association, you need to reword this question by saying, if you have a person, I guess to be politically correct here, a person within the study, but if this was if this was maybe more of a controlled experiment, you could say if you brought in someone from outside the study that weighed 20 pounds more than some other person, then how much taller would you expect that person to be than that other person? Then you could say 0.5 inches, about 0.5 inches. Okay? Is the RMS error of the line below around 0.1, 0.3, or 1? And then is it the regression line? Okay, so they're asking, what is the RMS error of this line here with respect to these data points? Well, what is RMS error? It's the sort of the average amount that these data points deviate from the line. With respect to this, we're usually assuming that this is the output variable on the y-axis. So this distance, and 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 this distance. All those distances taken together, if we kind of just think about their average, what's the average magnitude of those distances? Yeah, not just the average magnitude. So we don't care if this is negative and this is positive, just the average magnitude. Okay, well looks like it's going to be somewhere around, I guess here. Well, let's see. RMS is a little bit more than what we typically think about as average. So this looks to be about average, right in the middle. So maybe around here. Okay, so but it's not 3, it's 1. Right? 2 to 3 is 1. So 1. Now I'm looking at an answer key and they're saying 0.3. So 0.3 would be, this is 2.5, 0.3 would be here. How? I mean, if we just take, it looks like this is pretty symmetric above and below. So if we just think about, here's 0.3, 0.3, 0.3, so 0.3, 0.3, 0.3, 0.5, 0.5, 1.1, 1.1, 1.3, 1.7, 1.7. So 0.3 squared times 3 plus 0.5 squared, and then we'll do 2 times 0.5 squared plus 2 times 1.1 squared plus 1.3 squared plus 2 times 1.7 squared. Divide that by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then take the square root. Yeah, it's 1. I don't know what that answer key is talking about. Is this the regression line? So how do we answer this question? Well, okay, what they're going for here is we want to look and see, is there potentially another line which would go through the point of averages, which I guess you could say, let's just assume this goes through the point of averages, something like that. Is there another line that would potentially have a lower RMS? So I'm not sure how to answer that visually, but another perspective we can look at this from is what looks like to be the correlation coefficient of this. Because if it's a really low correlation coefficient, then you're going to get a close to horizontal line. If it's actually the correlation coefficient is 0, you're going to get a horizontal line. Because since there's no correlation, you just use the average y value as the regression line. So to me, I would say, yeah, this looks pretty unsymmetrical. It's close to a full circle. So I would say yes. A study is made of working couples. The regression equation for predicting wife's income from husband's income is shown here. Another investigator solves this equation for husband's income and gets this shown here. Okay, true or false and explain. The second investigator has found the regression equation for predicting husband's income from wife's income. If you want to compute anything, okay. So yeah, just true or false. Has the second investigator found the regression equation for predicting husband's income from wife's income? And if we want to compute anything, we'll use this here. So, okay. We know that for any general scatter plot, there's two regression lines, which means there's two regression equations, right? There's one if you treat the x-axis variable as the independent variable and the y as dependent, and then there's another if you treat the y-axis variable as the independent variable and the x as dependent. And so we can think about, let's just do husband's income here and wife's here. So what else do we know when it comes to these regression lines here? Well, we know that if we are treating the horizontal axis as independent and the vertical axis as dependent, then the slope is r sigma y over sigma x. So r 0.25 times sigma y is the wife's income over sigma x. 26, so the husband's 0.167. So that checks out. The slope checks out. Okay, now here we know it's going to be r sigma x, since that's the output, over sigma y. Let's see. 39. Yeah. Which that doesn't check out. So I'm just curious if we do this. Okay, yeah. So they just took the reciprocal of this 0.167 to get 6 here, but that's not correct. We know that's not correct because the reason why that's not correct is because you're not taking into account. So okay, you have r sigma y over sigma x, right? For the conventional x-axis is the independent variable, y-axis is dependent. But when you do it the other way, it's not sigma x over r sigma y, it's r sigma x over sigma y, because the whole purpose of the r is it accounts for the scatter. And so when the input is sigma y, so you go a certain position on the sigma y axis, and then for the dependent variable, the r is telling you, look, we're not going to go the full amount in the sigma x, the output variable. We're going to go a fraction of that to account for the scatter. So no, you don't just flip this to get the slope of the other regression line. So no, this is not correct. That's not going to be the right slope. So false. Okay, continuing with the same problem from the previous exercise. The couples in the previous exercise are followed for a year. Suppose everyone's income goes up by 10%. Find the new regression line for predicting wife's income from husband's income. Okay, so what they're going for here is that we want to think about. We've got the husband's incomes on the left, wife's incomes on the right. That's the x and the y variables. Okay, so we've got all these data points, right? to start out with before we got to this exercise. Now it's telling us that the couples in the previous exercise are followed for a year, and then suppose everyone's income goes up by 10%. So if something goes up by 10%, you can figure that out what the new value is by multiplying that value by 1.1, right? So the new data points we're getting are you're multiplying each of these by 1.1 and each of these by 1.1, which we know that's purely a change of scale. That's a change of scale. And so what do we know about changes of scale? We know that they don't change the correlation coefficient. Okay, but they will change the you want to multiply the averages by that factor you multiplied by, though. So the point of averages, let's see. So here's the original data. The point of averages, each of these values are going to be multiplied by 1.1. Well, actually, and the standard deviation are going to get multiplied by 1.1 as well. Yeah, if you add the same number to every number in the list, only the average gets changed. You add that same number to the average. Standard deviation doesn't change. If you multiply the same value by every number in a list, then the average and standard deviation get multiplied by that number, but the correlation coefficient doesn't change. So yeah, I'm not going to go through all that again, the changes of scale here, but we've got, so, okay, we're predicting wife's income from husband's income. So the new X average, and then we've got Y average, is going to be, so you've got 1.1 times the husband's income, and you've got 1.1 times the wife's income, average income. So 59,400, 36,300. Okay, now the same idea with the standard deviations. So 39 and then 26. So 42,900, 28,600. Okay, and then the correlation coefficient does not change with changes of scale, right? Okay, so now what's going to be the slope then of this new regression line? We just do R times sigma Y, 28,600 over sigma X. Okay, so it's the same slope, which makes sense because all we did was just scale up the two standard deviations, but the correlation coefficient didn't change. Okay, but it's not going to be the same regression equation because we're going to have different intercepts. So 0.1667. Okay, so, all right, we've got a point and a slope. So y minus y1 is equal to m times x minus x1. So, okay, we've got this times minus 59,400. Okay, now we're going to add to this 36,300. So what we're left with is y is equal to 0.1667x plus 26,400. So and there we go. Okay, a statistician is doing a study on a group of undergraduates. On average, these students drink 4 beers a month with a standard deviation of 8. They eat 4 pizzas a month with a standard deviation of 4. There is some positive association between beer and pizza, and the regression equation is, so the predicted number of beers is equal to, we don't know the slope, times the number of pizzas plus 2. However, the statistician lost the data and forgot the slope of the equation. Perhaps he had too much beer and pizza. Can you help him remember the slope? Explain. So, okay. Let's see. We've got the y, the output we'll say is the y is related to the beers drank. So, okay. That's, you've got y average is equal to 4. Okay. Then the standard deviation in the y they gave us as well, right? 8. Okay, now x average, which is the pizzas, is 4, and then the standard deviation in the x is 4. Okay. There's a positive association, so we know that R is positive. And now we need to figure out what the slope is. Okay, so we know that, so this is M, right? And we know that, let's see what we have here. We know that M is equal to R sigma Y over sigma X. So that's going to be 8 divided by 4 is 2, so this is 2R. So that's a start. So, okay, we can do, this is 2R. Okay, now let's see. Can maybe RMS help us? Because we know that RMS is the square root right? We have sigma y. We don't have r, but can we get the RMS? I don't think so. Okay, let's try this. Let's try and just create the equation from what we have here and see what happens. So what I mean by that is let's do the y minus y1 is equal to m times x minus x1. And let's see if this can help us to figure something out. So we've got y minus 4 is equal to 2rx minus 8r. So y is equal to 2rx minus 8r plus 4. So we could do this. Plus 4 minus 8r. Does that help us? Yes, it does, because 4 minus 8r, we can see that's the y-intercept, is equal to 2. So 2 plus 8r is equal to 4. 8r is equal to 2. So r is equal to 2 divided by 8. R is equal to 1/4. So 1/4 times 2 is 1/2. So there we go. We got the correlation coefficient, and then we also got the slope. Okay, an investigator wants to use a straight line to predict IQ from lead levels in the blood for a representative group of children aged 5 to 9. There is a weak positive association in the data. So true or false, and explain. All right, so let's make sure we have this straight. We want to use a straight line to predict IQ from lead levels. So we're predicting IQ from lead levels. For these children aged 5 to 9, there's this like weak positive association. So maybe something like that, right? True or false and explain. So, okay. And let's put the point of averages here. To do this, he can use many different lines. Yeah, true. You can use whatever line you want. You know, it's a free country, right? You can do whatever you want. You could use the horizontal line that goes to the point of averages. You could use the SD line. You can do whatever you want. Okay? He has to use the regression line. Well, no, just what we just talked about, because he can use many different lines. Okay, only the regression line has an RMS error. Absolutely not. Any line has an RMS error. You know, and in fact, when I said he could use many different lines, he doesn't even have to use a line that goes through the point of averages. He could use this line if he wanted to, and that's going to have an RMS. Okay, so any line he uses, yeah, same, just like the same question as before. Okay, now among all the lines, the regression line has the smallest RMS error. Now that's the big difference. This is why you could argue, well, why wouldn't you use the regression line if you're going to do this? Right? You could argue, yeah, he does have to use the regression line because that has the smallest RMS error. So this is the SD line, looks like. Regression line would be like that. That has the lowest RMS error, yes. Okay, in a large study, hypothetical study, of the relationship between parental income and the IQs of their children, the following results were obtained. Okay, for each income group, so they these different vertical columns, let's see, we're predicting, they haven't said what we're predicting, what from what yet, but okay, for each income group, these different income groups, the average IQ of children with parental income in that group was calculated and then plotted above the midpoint of the group. Sounds like a point of averages deal here, right? But you're not doing very small intervals. It was found that the points on this graph followed a straight line very closely. The slope of this line in IQ points per dollar would be about. So, okay, let's think about this, because I wonder if this is like a trick question. So we've got, let's put the income of the parents on the horizontal, that's going to be the input, and then the IQ on the output. And then they've broken up the incomes into, oh, it says etc. Okay. So this is different. 0 to 10,000, 10,000 to 20,000. So, okay, these are some pretty small groups. So you can assume the income goes from 0 to, 150,000 or something like that. So they've broken it up into smaller groups than I initially thought. I didn't see it said etc. there. Okay, and now what they're saying is that for each of these groups, they calculated the average IQ score of all the children within these groups and then plotted it in line with the midpoint of the interval. This is what they're talking about is you have a point of averages graph. That's what they're talking about. And so it says it was found that the points on this graph followed a straight line very closely because, yeah, the points of averages, the literal points of averages, aren't necessarily going to be collinear. But the regression line is going to go through those points as closely as possible. It's going to try and fit to those points as closely as possible. So this is the regression line, what they're talking about here. This is the regression line with respect to income being the independent variable and IQ being the dependent variable. And so with the slope of the line then is, okay, it says it was found that the points on this graph followed a straight line very closely. The slope of this line would be about, because they're saying, it's like they're saying they didn't technically do regression. They're just saying this line was close to a straight line, all the points, and they kind of estimated what that line is. That's going to be close to the slope of the regression line. So what's the slope of the regression line? That's just going to be R times sigma Y, which is IQ, divided by sigma X, 45 So let's see. So what's 7 plus, let's do this. 7 plus 1/2. Wait. Okay, hold on. Let's do R is 1/2 times sigma y divided by sigma x. 1 over 6,000. Yeah. One child in the study referred to in the previous exercise had an IQ of 110, but the information about his parents' income was lost. At $150,000, the height of the line plotted in exercise 9 corresponds to an IQ of 110. So is $150,000 a good estimate for the parents' income, or is the estimate likely to be too high or too low? All right, so what they're talking about here is, let's see. So we've got some scatter plot here. It's about 0.5. Okay, here's the point of averages. So you had a child in the study had an IQ of about 110, which is like a little bit below average. So like right here. Okay, there's the 110. But the information about the parents' income was lost. And so they're saying at $150,000, the height of the line plotted in the previous exercise corresponds to an IQ of 110. So would that be a good estimate for the income? I guess it might be okay, but no, technically it's not the best estimate because remember, we've got, so here would be like the SD line running symmetrically through the ellipse. Okay, then the regression line with respect to income being the independent variable is going to be shallower than the SD line. Okay, but when you've got if you're doing the regression line with respect to IQ as the independent variable, then it's going to be steeper than the SD line. And so what they're saying is that okay, let me redraw this. That wasn't the most accurate. So something like this, still shallower. And then you got something like this, maybe. Okay. So the 110 here, they're saying we lost information about the income of the parents, right? But we know the IQ. So they're saying, okay, well, could you do this as a prediction for the income of the parents? And yeah, I mean, I guess you technically could, but the best estimate, if you're going to try and make an estimate, would be this. You go to this regression line. You go here. So it's going to be too low in general, which is kind of weird to think about. It's like how could the regression predictions be different, but it's just kind of the way it is, right? The best you can do is predict the averages within that input interval. Whatever of all the data points within that input interval, what's the average of those data points? That's the best you can guess. So it's in general, it's going to be too low in this case. Okay, hypothetical. A congressional report is discussing the relationship between income of parents and educational attainment of their daughters. Data are from a sample of families with daughters age 18 to 24. Average parental income is $79,300. Average educational attainment of the daughters is 12.7 years of schooling completed. The correlation is 0.37. All right. The regression line for predicting daughters' education from parental income is reported as y equals mx plus b, with x equal parental income, y equal predicted education, and here's the slope, and here's the y-intercept. So there's the equation. Is anything wrong, or do you need more information to decide? Explain briefly. All right, so let's just go through this. Well, actually, hold on. Let's write out what we've got here. So we're predicting education from income. So the x average is the parental income, $79,300. The y average is the average educational attainment, so 12.7 years. Okay, do they give us anything about standard deviation? No. So we've got R is 0.37. Okay. So let's see. What would... Is there maybe a negative in here that shouldn't be there? Because we know sigma x and sigma y can't be negative. So since R is positive, there shouldn't be any... Well, no, there could be negatives because you're subtracting the 12.7 years. Let's just write this out. Okay, so y minus y1 is equal to 0.37 sigma y over sigma x times x minus 79,300. Okay, so y minus 12.7 is equal to 0.37 sigma y over sigma x times x minus, and then let's see, 0.37 times 79,300, 29,341, 29,341 sigma y over sigma x. So we've got y is equal to 0.37 sigma y over sigma x times x. Then we want to do plus, and then 12.7 minus 29,341 sigma y over sigma x. Okay. Does that help us? So, okay, well, let's see. If this is m, if this, let's come here. If this is, if m is r sigma y over sigma x, then we can take m divided by r, the m that they gave us divided by r. So we can do 0.00000, 1, 2, 3, 4, 5, yeah, 925 divided by 0.37. So there's sigma y over sigma x, 0.4025. Okay, so let's just see if it checks out with the y-intercept. So there's sigma y over sigma x. Let's multiply that by negative 29,341. And now let's add that to 12.7. So that doesn't look like it matches up with what it's supposed to be. Did I mess something up here? So let's see. We've got y minus y1, okay, is equal to m 0.37 times sigma y sigma x times x minus x1, then 0.37 sigma y over sigma x times x minus, and then 0.37 times 79,300, 29,341. Then you added 12.7 to both sides and got that. Okay, now we use the m they gave to get sigma y over sigma x. You just divide both sides by r to get sigma y over sigma x. So did I count this right? 1, 2, 3, 4, 5 zeros. That divided by the r. There's sigma y over sigma x. So if we multiply that by 0.37, we're obviously going to get, or no, we're going to get the slope. We just did that, right? But it's really more about, does it match up with what the y-intercept is supposed to be? This is the y-intercept, so you multiply that by minus 29,341 and get that. Now do 12.7 plus that. And no, so something's wrong. Okay, many epidemiologists think that a high level of salt in the diet causes high blood pressure. Intersalt is often cited to support this view. Intersalt was a large study done at 52 centers in 32 countries. Each center recruited 200 subjects in 8 age and sex groups. Salt intake was measured, as well as blood pressure and several possible confounding variables. After adjusting for age, sex, and other confounding variables, the authors found a significant association between high salt intake and high blood pressure. However, a more detailed analysis showed that in 25 of the centers, there was a positive association between blood pressure and salt. In the other 27, the association was negative. Do the data support the theory that high levels of salt cause high blood pressure? Answer yes or no and explain. Okay, so let's go through this again. You have many epidemiologists think that a high level of salt in the diet causes high blood pressure, and Intersalt agrees with this based on their study here. You've got these 50, so they're thinking that high levels of salt in the diet cause high blood pressure. So you have 52 centers in 32 countries. Each center recruited 200 subjects in these 8 different age and sex groups. Okay, 200's a lot across these 52 centers in 32 countries. That's pretty spread out. Okay, salt, and then you have these different age groups and sex groups. Salt intake was measured, as well as blood pressure and several possible confounding variables. Okay, sounds good. After adjusting for age, sex, and other confounding variables, which they can do because they've collected data across these different age groups, the authors found a significant association between high salt intake and high blood pressure. Okay, so but what's the association, right? However, a more detailed analysis showed that in 25 of the centers, 25 of the 52, so it's more than half, or no, a little bit less than half, there was a positive association between blood pressure and salt. In the other 27, the association was negative. Do the data support the theory that high levels of salt cause high blood pressure? So, okay, if there's a negative association or a positive association, what exactly is that saying again? Well, that's just saying that, okay, if there's a positive association, then the higher the salt in the diet, the higher the blood pressure. If there's a negative association, then let me make sure I've got that right. So you've got the salt intake and the blood pressure. If there's a positive association, the higher the salt intake, the higher the blood pressure. If there's a negative association, then the higher the salt intake, the lower the blood pressure, which is kind of counterintuitive, but to me that would be more of saying that there's confounding variables, right? This isn't necessarily saying that, oh, you eat more salt, you're going to lower your blood pressure. I mean, I guess it could be, but yeah, to me, this is an issue. The fact that there's a negative association in 27 of the centers, that's how they could try and deceive people by just making a general statement that, let's see, the authors found a significant association between high salt intake and high blood pressure, right? So what they could do is how could they say this? Well, maybe they just take the average of all of the associations and get like a 0.7 average and say, look, there's an average 0.7 positive association, which, maybe that's legitimate, but it's not so much when you think about that there was a negative association in, if it was just a few of the centers, then okay, but close to half, it just makes you wonder. This negative association is suggesting that there's no really association, because you have people with these high salt intakes that actually their blood pressure is lowering, which again, it doesn't make you think that you want to eat more salt to lower your blood pressure. It just makes you think that it doesn't matter whether or not you eat more salt. Because look, there's people eating in half of the centers, there's a negative association, which is saying that if you eat more salt, your blood pressure is lowered. So it's in essence saying there is no association. So to me, this is an issue. More than half of the centers, they applied a correlation coefficient. I guess if we're assuming the data is homoscedastic, football shaped, so that means the correlation coefficient was applicable for more than or close to half of the centers. There was a negative correlation coefficient. It's too many centers, right? If it was just a few centers, but the rest were positive, then maybe so. But close to half, that's an issue.